So if you guys could turn to the slide that says misconception question number 3, we're going to wrap up this week by looking at a kind of interesting question. And the question says, a satellite in circular orbit around the Earth moves at a constant speed, right? So here's Earth, and you have some kind of satellite moving at a constant speed around it, as a satellite does, okay? This orbit is maintained by the force of gravity, right? There is a gravitational force that's always pointing towards the Earth no matter where the satellite is, okay? And that's what allows centripetal force to exist, right? That force of gravity is the centripetal force. That's the force that's keeping it in the circle, okay? But here's the thing about the satellite. That gravitational force does no work, okay? How is that possible? All right, A, no work is done if there's no contact between objects. Well, that's not true. That can't be possibly true because if I just drop an object, right, gravity is not touching it, but it sure is doing work as it's going down, right? Gravity will do work on a stone or a ball or something that's dropped from some height. So can't be A. B, no work is done because there is no gravity in space. Erroneous, no way. There's obviously gravity. Gravity is what is keeping the satellite in orbit, right? C, no work is done if the direction of motion is perpendicular to the force. Now that seems like we might be getting somewhere, okay? Because here's the deal. Remember I said that velocity, right, is always tangent to the circle in the circular motion problem, right? Whereas the centripetal force or centripetal acceleration is always pointing towards the center. That is a 90-degree angle, right? So any little baby displacement done along this circle here, right, is always going to be perpendicular to the gravitational force. So in other words, if work is equal to force times displacement, right? Well, the gravitational force in this case and the displacement times cosine theta, theta will always be 90 degrees, right? And if theta is 90 degrees, that is a big fat 0, so that there's no work being done, okay? And just to round out our options here, it says no work is done if objects move in a circle. Yes. If there is a circular force accelerating something around a circle, you can have work being done by that circular force. If there's a torque rotating something about some pivot point, you can do work about that pivot point, okay? We'll get there in a later chapter, but for now, just know that if velocity, hence displacement, right, is perpendicular to the gravitational force, you can never have work being done. And so strangely, even though this guy's whipping around again and again and again around this planet, right, gravity's never actually doing work on the satellite. So just to kind of summarize, we introduce energy this chapter, and we've talked about many different types of energy. We've talked about how energy is like a currency that gets stuff done in the universe, and you could think of the universe as this like almost like a Wall Street, just everyone's like wheeling and dealing and just trading different types of energy with each other, and making stuff happen in the world, all right? That stuff happening could be everything from a stone falling from a height. It could be anything from a spring releasing and you have some sort of motion that comes out of that. It could be planetary motion. Everything that you see has some sort of energy and energy interaction associated with it, okay? In the next week, we're going to be focusing on one particular aspect of this kind of exchange of energies, and that is the principle of conservation of energy. And it's really my fave, just going to say it. It's my absolute favorite thing to learn and teach in physics because I think it's so powerful and so elegant and is able to predict so much. And I look forward to seeing you there next week. Signing off.